Hello everyone, welcome to our differential equation class. In this video we are going to use the Laplace transform method to solve differential equations with generalized sources. First we are going to introduce the type of generalized sources we are interested in, which are called impulsive forces. Then we're going to see that a mathematical description of these impulsive forces is given by Dirac's delta generalized function. And then we are going to solve differential equations, initial value problems that have these Dirac Delta generalized functions on the right hand side of the equation as a source. So that's the plan for today. Let's start introducing the particular type of generalized sources we are interested in, and these are impulsive forces. Maybe the simplest example of an impulsive force is the force done by a hammer when we hit a pendulum. The action of this force happens at a particular point in time, so let's call that time t0. And the intensity of the force is very large, so we approximate that by infinity. A force with these two properties has a graph that looks more or less like this. So the intensity of the force is 0 until we reach the time t0 when the force is acting, and the intensity of the force at that particular time is infinity, and then the intensity of the force drops back to 0. Although the intensity of the force is infinity, we know that the amount of momentum and energy transferred to the system by the force is finite, because after we hit the pendulum with the hammer, we see that the pendulum is oscillating back and forth with finite energy and momentum. So another property of impulsive forces is that the amount of momentum transferred to the system is finite. So an impulsive force has an interaction time that is a single point in time, the force intensity is infinite, and the momentum transfer to the system is finite. Let's recall what is the momentum of a system. The momentum of a system with velocity v and mass m is the product, mass times the velocity. And when we talk about the momentum transfer, what we mean is that the variation in momentum, so delta, variation of mass times velocity, is the mass times the velocity at the final time minus the mass times the velocity at the initial time. And of course, this is nothing more than the integral in time from the initial time t initial to the time t final of mass times the acceleration of the object, integral in time. And because of Newton's equation of motion, this is the integral from t initial to t final of the forces acting on that system. And then what we are saying, when the amount of momentum transferred to the system is finite, what we are saying is nothing more than this integral has to be finite. So this is the characterization of an impulsive force. Interaction time, one single point in time, force intensity infinity, and momentum transfer finite, and by that we mean this integral has to be somehow defined for the impulsive force, this integral here, and has to be finite. A mathematical description of an impulsive force is what is called the Dirac Delta generalized function. Although it's called Dirac Delta, the properties of this generalized function already appears in works by Joseph Fourier in 1822. Then we have formulas for unit impulse functions that were already used by Cauchy in 1827, and many others that includes Poisson, Kirchhoff, Helmholtz, Kelvin, and Heaviside. But this generalized function is called Dirac's delta because Paul Dirac used it in quantum mechanics, in his studies of quantum mechanics in 1926. So that's why we have the name of this generalized function associated to Dirac. Although Dirac's delta was rigorously defined only by Laurent Schwartz in 1945. Anyway, what is the Dirac's delta? Well, here is one definition. There are several ways to define this generalized function. This is one way. Dirac's delta, generalized function, is a limit of a sequence of functions. So this is Dirac's delta, is a limit of a sequence of functions. And what are these functions here? Well, they are given by this expression. Delta n is a function that is the difference between two steps multiplied by a scaling factor, and this is the index in the sequence. So n takes values 1, 2, 3 up to infinity. We take the limit, n goes to infinity, of these functions, and whatever we get, that is what we call Dirac's delta generalized function. So let's start trying to understand this definition a little bit. So let's put n equal 1 here. So we are going to have the first element in the sequence of functions that we use to define the generalized function Dirac's delta. So n equal 1. So we put a 1 here, so we are going to have 1. So essentially it's the step at 0 minus the step at 1. All right. So what we want to understand is this element in the sequence, which is the step at 0 minus the step at 1. So here we have the picture of that. The step at 0 is in orange. This is the function step at 0. And then we have the step at t equal 1. This is the function. Now if we make the difference between these two, here 0 minus 0 is 0. Here is 1 minus 0, so it's 1, the difference, that difference. And then over here, the difference is 1 minus 1, so becomes 0 again. So we end up with the difference of these two steps is a function like a bump function given by 0, 1, and then back to 0. So this is the function delta 1 when we put n equal 1. What happens when we put 2 and 3, and so on? Well, the result is here in this picture. Here we have, let's review, here we have the delta 1 that we found before. Now what happens when we put 2? When we put 2, then we need to do the difference between the step at 0 minus the step at 1/2. So here is 1/2. Let's put this in the right color. Let's put that in color. So here we have the 1/2. So the function is 0 everywhere else between 0 and 1/2, and in between 0 and 1/2 the function takes value 2, so we go a little bit higher. So that is delta 2. What happens when we put n equal 3 here? Well, it's right here, the result is 3, and then we need to do the difference between the step at 0 minus the step at 1/3. 1/3 is closer to 0 than 1/2, so the function we are going to obtain is 0 and everywhere except between 0 and 1/3, and in between these two, in this little interval 0 and 1/3, the function takes value 3, so we go a little higher now. And this is delta 3. And you see what is going to happen when we increase the value of n. This region where the function is different from 0 is going to 0. This is always 0, over here is always 0, and here we are going to 0, and the function takes value higher and higher, the higher the value of n. So we have an interactive graph to see these different functions delta n all together. Let's go to that. Here we have the function delta 1, and now if we move this slider here, you see what is happening when we increase n. The function gets thinner and taller, and in the limit we are going to obtain the Dirac Delta generalized function. So 0 everywhere except at the one point that is infinity. So the limit n goes to infinity of this sequence is what we call Dirac Delta generalized function. Notice that we have defined this Dirac Delta as function of t, but we can translate all these functions to the right by c or to the left by c, and then we get what is called the translations of the Dirac Delta. So and we denote it like this: the translation by c of the Dirac Delta generalized function is the limit of the translations of the individual functions in the sequence that defines the Dirac Delta. So let's see that in an interactive graph. Here we are in our interactive graph. Recall this is the sequence that defines the Dirac Delta, and what we can do now is the whole sequence we can move it to the right or to the left, and then take the limit, and then we have the Dirac Delta shifted by this value, by 2 for example, or shifted to -3. So here we have the sequence and defines the Dirac Delta shifted by 3, by -3, and we can go over here for example and get the Dirac Delta shifted by +3. So these are the shifted versions of the Dirac Delta generalized function. These translations of the Dirac Delta have the same property as the original Dirac Delta. For example, the Dirac Delta translated by c is identically 0 for t different from c, and this Dirac Delta translated by c is infinity when t is equal c, so the graph looks more or less like this. These are the main two properties of the impulsive forces, but there is a third property that is related with the transfer of momentum to the system being finite. What happened with that property? Do we have that property on the Dirac Delta? To see if we have that property or not, let's go back to the definition of the Dirac Delta as the limit of this sequence of functions, and here we have these functions again. And notice one important property of these functions. Consider delta 1, the first element in the sequence, is this function here. What is the integral of this function in the real numbers? Well, it's the area under the graph of the function. The function is identically 0 here and here, so the area under the graph of the function is only coming from this part of the function, which is the area of this square. And this square has size 1 and 1. So this function has integral equal to 1. So the area under the graph of the function delta 1 is 1. Now consider the function delta 2. Delta 2 is a higher function. So first of all, delta 2 is this function here. Function is delta 2 is 0 everywhere else except in the interval 0, 1/2, and in that interval takes value 2. So the area under the graph of that function is the area of this rectangle of size 2 and 1/2. So again, this integral is going to be 1. The area under the graph of the function is 1. And finally, go to delta 3. Delta 3 again is 0 everywhere except in the interval 0, 1/3, and in that interval it takes value 3. So the integral of the function is the area of this rectangle, which again is 1. So in general, it can be proven, it's not difficult to see that the integral of any element in the sequence delta n, shifted or not shifted, integral where the function is different from 0, for any value of n, by construction, this is 1. So now that we have this property, we are going to try to see if we can define now what is the integral of the Dirac Delta generalized function, knowing that we have these properties for each element in the sequence that defines the Dirac Delta. So the idea now is that we are going to define, this is a definition now, the integral of the generalized function Dirac Delta of the limit as the limit of the integrals of every element in the sequence. So this is how we define the integral of the limit of a sequence of functions, as the limit of the integrals of each element in the sequence. We have to define the integral of the Dirac Delta in this way because we cannot define the integral of the Dirac Delta, we cannot define it as in the same way as we do with functions by the limit of Riemann sums. Recall, when we have a nice function, a continuous function like this one, f, in the interval ab, we define the area under the graph of the function as the limit of Riemann sums, and where we are adding areas of little rectangles, and we introduce more and more rectangles, and we get the exact area under the graph of the function. This is the procedure done by Riemann, and it's called Riemann sums. But certainly we cannot do it here. There is no way we can do that Riemann sums here, so we need to do something else, and what we do is this. We introduce the definition of the integral of a limit of a function as the limit of the integrals of each element in the sequence that defines that function. With that definition and this property we have seen before, that we do it by construction on the sequence, we have then the main result that the integral of the Dirac Delta around the singularity is 1. So this property is the property that encapsulates in mathematical terms that the impulsive forces transfer a finite amount of momentum. One last comment on Dirac's delta is that we use a particular sequence to define the Dirac's delta, but actually there are many sequences, delta n, that define the same limit that we call Dirac's delta, and we are going to show in an interactive graph a few of these other sequences. Here we are in our interactive graph. Recall that this is the sequence that we started with. We can shift this sequence anywhere we like, and we have the limit as the Dirac's delta. And here we have another sequence that also has the limit to be the Dirac's delta. Is a very similar sequence as before, but now is centered around 0. Before it wasn't centered, and now we have a sequence centered around 0. Of course, we can shift all these sequences anywhere on the real line. But it's very similar to the previous sequence. But now we can use Gaussian functions, something like this. And then we can also define Dirac's delta with a function that is continuous. And you see this function is going to give us the Dirac's delta because both have areas integral 1. You see the Gaussian and the step functions in blue have we can see that they have the same integrals, and we can use also different functions. So for example, let's get rid of the step, and we can put polynomials. Polynomials looks very much like Gaussian functions, but the Gaussians go to 0 much faster than the polynomial, but still the polynomials are thinner, near 0. And because of that, they have the same property as of area 1 as the Gaussians have. So we can use polynomials, we can use Gaussian functions, which are some type of exponentials, and we can use trigonometric functions. So let's get rid of the Gaussian, for example. Polynomials, trigonometric functions, for example, sine of x over x, would do the trick with some appropriate normalizations. You see, the function doesn't need to be positive to have the limit to be the infinity at equal 0 and area 1. All these functions have the same properties. The polynomial, the Gaussian function, the trigonometric functions, and the step functions. So there are infinitely many sequences we can use to define the Dirac Delta generalized function. Now let's move on to one of the most important properties of the Dirac Delta, that is the following. If we have a function f of t, so let's say here f of t, and suppose this function is continuous on some interval ab. Now what is the integral between this a and b of the function f times a Dirac delta that is shifted by c, and we have c inside the integration region. So the Dirac delta is singular inside the integration region. What is this equal to? So in order to see what that is equal to, we are going to do the following. We are going to do the calculation, and the calculation is integrate from a to b the function f of t delta t minus c dt, and this is equal to, and what is that equal to? Well, recall we have a definition for the integral of a Dirac delta, and that definition means, let's put it down here, that we need to take a limit when n goes to infinity of integrals of whatever is what you are integrating, in this case f of t, times the elements in the sequence of function that defines the Dirac delta, delta t minus c dt. This is what we need to integrate. And recall what is delta n t minus c. What is this? Well, let's write it down. This is the limit. N goes to infinity. The integral from a to b. This is all the same as before, f of t. But here what we need to write is, what are delta n? Delta n is n, and then we need to multiply a step, sorry, this is a step, at shifted by c, and then minus the step shifted by c minus 1 over n. All that dt. So that is what we need to use for delta n, is the delta n shifted by c. But notice that this function, I have a little graph here of this function over here. This function is the same function we were using, this bump function, but between c and c plus 1 over n. This is what this function is. So notice that this function is 0 up to c, and is 0 after c plus 1 over n. And in between, it takes value 1. So if we use that those properties in this integral, so let's put that in writing. This function here, the step, recall we need to multiply that by n later, so by this n here. But this function is equal 1 in the interval c plus 1 over n, and this function is equal 0 outside that interval. Outside this interval. All right. Then if we use that property, then what do we have here? What we have is the limit. The limit still stays there. N goes to infinity. And now we need to integrate only from c to c plus 1 over n. And what do we need to integrate? Well, f of t, we have the n. And now this function, recall, takes value 1 in that interval, dt. So n, of course, goes outside. So we have limit. N goes to infinity. And we have an n here, so that n goes to infinity. And then we have an integral on a very small interval from c to c plus 1 over n. This is a very small interval of the function f of t dt. Okay, what is that? In order to see what is happening here, it's better to introduce a new notation, which is the function big F of t, which is going to be the antiderivative, any antiderivative of small f dt. Because if we do that, with that notation, the integral from a to b of the function f of t delta t minus c, which is what we are computing, this is the limit n goes to infinity. Recall we have n here, and this is because of the fundamental theorem of calculus and that definition, this is nothing more than the antiderivative evaluated here minus the antiderivative evaluated there. So this is nothing more than the antiderivative evaluated at c plus 1 over n minus the antiderivative evaluated at c. Okay, but now let's call h to be 1 over n. Because we have this 1 over n here, we are going to call it h. But here we have n, so this is 1 over h. Okay, so let's do these changes. And what happens in the limit? Well, if this n goes to infinity, then h goes to 0, isn't it? So this is the same as the limit h goes to 0 of 1 over h, that is the n, and then we have here f at c plus h minus f at c. And let me write this h over here and move this a little bit over there. And what do we have here? This limit is nothing more than f prime at c. But f is the antiderivative of small f, big F, so this is just f at c. And this is what we wanted to compute. So the integral of the Dirac delta multiplied by a function in an interval in a region of integration where the Dirac delta is singular returns the value of this function at that particular point. So then this is actually a proof of a theorem. So we are going to put here proof. And we are going to put the result we found here, that the integral of a function times a Dirac delta is just the function evaluated at the point where the Dirac delta is singular, if and only if this point belongs to the region of integration. So this is the main property, a very important property of the Dirac delta. This theorem is very useful to compute many other things with the Dirac delta. For example, the Laplace transform. What is the Laplace transform of a Dirac delta? So let's compute it. So the Laplace transform of Dirac delta shifted by c is going to be equal to the integral from 0 to infinity of exponential negative st, and then we have our delta t minus c dt. But this is a particular case of what we saw before in the previous theorem. In the previous theorem we said, suppose if the intervals in the previous theorem is 0 infinity, and we call the function g, the function f, we call it g. The previous theorem says, oh, if the singularity is in the interval in the region of integration, then you're going to get the value of this function at the singularity point. Of course, if we didn't say it, but if the singularity is outside the integration region, we are integrating the function g times 0, because Dirac delta is 0 in that case, so of course we are going to get 0. So the previous theorem says this. With any function, continuous function g, what happens if the function is exponential negative st? Well, then what we are going to get is that this is going to be equal this function exponential negative st evaluated t equals c, so negative sc, and this is only for c bigger or equal 0, and or the other possibility is 0 for c negative. Well, this is what we need to write here. The Laplace transform of the Dirac delta at t minus c is going to be minus cs for c positive as any real number, and then we are going to get 0 for c negative, and then this little calculation becomes a proof of that result. So, and that's it. There's nothing else to do. We use the previous result to compute the Laplace transform, and we can do even more general calculations. For example, this one here. What is the Laplace transform of any function times a Dirac delta? What is that equal to? Well, let's write it down. What we are actually doing when we compute the Laplace transform of a function f of t times the Dirac delta t minus c. Well, this is the integral from 0 to infinity of exponential negative st, the function f of t, then the Dirac delta t minus c dt. But again, this is a particular case of the previous theorem, because recall, this is the previous theorem with any function g. So what about if g now is this product? Then we can use this same result and say that this is going to be equal the function g, which in this case is exponential negative c s evaluated at t equals c. So we put c here, and then f at c for c positive or 0, that is when the singularity is inside the integration region, or is going to be equal 0 when c is negative. And that's all there is to this calculation. It's a particular case of the previous theorem. Here we put exponential negative cs f at c, in this case in c positive or 0, or 0 when c is negative. And that's all. These two results are straightforward results from the main result in the previous page. Let's use all we know about Dirac delta to solve an initial value problem with a generalized source. For example, this problem where we need to find the solution of this equation, and let's see what we have. On the left side, it looks like the equation of a spring with spring constant 25 oscillating without friction, and on the right side we have an impulsive force that is proportional to this Dirac delta with this proportionality factor, and the impulsive force is acting at the time t equal pi, and we don't have any initial condition, so 0 initial position and velocity. So let's see how this spring is going to move. Solution. So what we need to do is write down the equation for the spring, which is y, let's put it here, y double prime plus 25y, and this is equal, we have here 2 cosine of t times the impulsive term delta t minus pi. Alright, what do we do? Well, we compute the Laplace transform on both sides. So on the left side, what we are going to get is, because of the linearity of the Laplace transform of the second derivative plus 25, the Laplace transform of the function y. And what do we have on this side? Well, we have a function times a delta and the Laplace transform of that. We have a result for that, which is this. The Laplace transform of any function times a Dirac delta is exponential negative cs, where c is where the Dirac's delta is singular, and then we have to evaluate this function at that c. And we do that because our c, which is pi, is in the integration region. So this is going to be 2 cosine, and now we need to evaluate at pi, and then we need to, the Laplace transform is going to create here, of the Dirac Delta, is going to create a negative pi s, and that is the right hand side. On the left side, if we come back here, because we don't have any initial condition, they are 0, so this is just nothing more than s squared, the Laplace transform of y, and here is 25 Laplace transform of y. And now if we recall that the cosine of pi is actually -1, then this is just -2 exponential minus pi s. So we can pull common factor from the first two terms, the Laplace transform of y, and this is what we get, and over here we have -2 exponential minus pi s. So we computed the Laplace transform of the solution we are looking for, which is exponential minus pi s, and then we have -2 over s squared plus, let's write it down as 5 squared. So now we need to compute the inverse of this Laplace transform, but let's recall one thing, that the Laplace transform of the sine of at, well, this is very similar to what we have in our problem. This is a over s squared plus a squared. So what happens for this Laplace transform when we use a equal 5? Well, we are going to get almost what we have here. The problem is that we don't have 5, we have this factor. But this is not a problem, because now the Laplace transform of y can be written as, let's put the -2 over here. Let's put the exponential over here, pi s. And now we have 1 over s squared plus 5 squared. So what if I multiply by 5 and I divide by 5? And now I look only at this part. Well, this is exactly that for a equal 5. So what we end up with is -2/5 exponential minus pi s, the Laplace transform. Let's make a little bit of space here. The Laplace transform of the sine of 5t. We are almost there. Now we need to remember one of the translation identities. Let's write it down here. Whenever we have an exponential negative cs and the Laplace transform of a function we know, this is nothing more than the Laplace transform of the shifted version of the function times a step. So if we use that property in our problem, we end up that the Laplace transform of y is nothing more than -2/5 the Laplace transform of a step t minus pi, and then the sign shifted, sine of 5 shifted t minus pi. And we found the solution of our problem. This is going to be -2/5 the step t minus pi, which means that the solution is identically 0 until the time we hit it with the impulsive force, and after that the spring starts oscillating like with a sine function. And that is the solution to our problem. So this is how we can use Laplace transform to solve problems with impulsive forces. Let's finish this video with a couple of remarks. The first one is that the solutions to second order linear differential equation with a Dirac Delta source, they have a particular name. They are called impulse response functions. So let's write down this definition in a little bit more precise way. So let's suppose we have L of y, Well, L of y is a linear operator of the form second derivative, first derivative, function, so second order linear operator that appears in second order linear differential equations, so something like this. Suppose we have that operator, then the function y delta, solution of the initial value problem given by the operator on the function equal Dirac delta shifted by c, with 0 initial conditions for the function and the derivative. That solution is unique and is called the impulse response at the time c of the operator L. So what we have here is that we have the operator describes, for example, a system, for example, a mass spring system or a pendulum, and this describes an impulsive force that is acting on the system, and this is how the system is going to behave, the solution, when we don't have any other initial condition. All we have is the impulsive force. So all we have is an impulsive force that acts on the system. For example, we hit the spring with a hammer at the time t equals c, and the spring is going to move, and it's going to move in response to the impulsive force in a particular way. That way is the impulse response solution. There is a formula for the impulse response, of course, because we can solve this problem in the same way we solved the previous problem. Recall the previous problem. We can also solve this problem when the right-hand side is simply Dirac delta. And how we do it? In the same way we did it before. So we compute the Laplace transform on the left side. Recall the L is a linear operator, so we have the second derivative of this function plus a1, the first derivative of this function, plus a0, the original function, all that Laplace transform, and has to be equal the Laplace transform of the delta, t minus c. But we have a formula for this right-hand side, which is exponential negative cs. And because we have 0 initial conditions, what we have on the other side is nothing more than s squared plus a1s plus a0, all multiplied by the Laplace transform of the function we are looking for. So let's recall that what we have here is the characteristic polynomial of the linear operator. This is p of s. Alright, so this is the formula. The Laplace transform of the impulse response function has to be the exponential negative cs over the characteristic polynomial of the operator. And that's it. This is the formula. And well, we cannot do more than that because we don't know what the operator is. We don't know the coefficients a1 and a0. So the most we can do is write it like this, or saying that the impulse response is whatever is going to be after we invert this Laplace transform of exponential negative cs over the characteristic polynomial of the operator. So this is another way to write down the solution. Until we know the operator, we cannot do more than this. Okay? So to have a little bit of more physical intuition of how this function looks like, what this impulse response is, let's solve the next problem, which is our last problem for this video. So this problem is going to give you an interesting characterization of the solution impulse response. As before, suppose we have a linear operator of this form, and now we are going to show that these two functions are the same. What are these two functions? On the left, we have the impulse response function. Here it is. That's why I'm calling it y delta. And y delta, this is the function we want to understand. And to help us understand that, we see that this function is exactly the same as this other function, yh. What is this h? Well, this yh is the solution of this initial value problem. Notice that we have no sources. There is no hammer here. acting on this system. And the initial condition is 0 initial position, but we have a non-zero velocity at time t equals 0. Notice here that the Dirac delta is at t equals 0. So these two functions are the same. So that gives us a characterization of what is the impulsive force. The action of the impulsive force on a system is to provide an initial velocity to that system. So that is the physical interpretation of what is the impulse response. It gives an instantaneous velocity to the system because these two functions are the same. This is what we are going to prove now. Once we prove it, that's it. Okay, so what is the calculation we need to do? Well, we need to solve these two problems with the Laplace transform, these two problems. We already have solved this problem, but let's do it again to have it on the same page. Solution. So let's recall that the characteristic polynomial of the operator is going to be s squared plus a1s, this is an s here, plus a0. So with that in mind, let's solve the first problem, this one here. So the Laplace transform of y delta double prime plus a1 y delta prime plus a0 y delta, the impulse response function, and on this side we have the Laplace transform of the Dirac delta, and now is at t equals 0. So, well, then this is equal 1 because exponential, recall here, let's go back here, we have c equals 0, so this is 1. So what we are going to have over here is just 1. And on the other side, we are going to have the characteristic polynomial, so we are going to have s squared plus a1s plus a0, which we just call the characteristic polynomial, and here is the Laplace transform of y delta. So from here we get that the Laplace transform of y delta, when the Dirac delta is at t equals 0, is nothing more than 1 over the characteristic polynomial, p of s. And now we are going to see that the other function, yh, has exactly the same Laplace transform. So now, this is problem 1. Now let's go to problem 2. Problem 2 is we want to find the solution of yh double prime plus a1 yh prime plus a0 yh. And that is equal 0 now. So what do? We compute the Laplace transform. Let's change the color so it's looking a little nicer. We compute the Laplace transform here, and of course we compute the Laplace transform on the other side, but now the Laplace transform here is actually 0. Okay, so we have 0 here, and now we have the Laplace transform of the second derivative of h plus a1, the Laplace transform of the first derivative of h plus a0, and we are going to need a little bit more space. Oops, that is not so nice. We are going to need more or less that space. Laplace transform of yh, all that equals 0. But now, recall, we have initial conditions, so this is 0, but this is different from 0. Okay, so let's use the properties of the Laplace transform. This is equal s squared, the Laplace transform of yh. And now we have minus, now we need the s times the function at 0 minus the derivative of this function at 0. Okay, this is the first term. Then we have a1 that multiplies s, the Laplace transform of the function yh, minus yh at 0, and then plus A0, the Laplace transform of YH. And all that equals 0. But here is that we use the initial conditions. This is 0. This here is 0. But here we don't have 0. We have equal 1. So we end up with S squared plus A1S plus A0, Laplace transform of YH. And now we have minus 1 equals 0. Recall this here is, well, let's put it in red. We are doing it in red, so let's be consistent. And this is P of S. So what we end up with is that P of S, the characteristic polynomial plus the solution YH minus 1 is equal 0. Well, we move the 1 to the other side. We divide by the characteristic polynomial, and this is the Laplace transform of YH. And as you see, it's exactly the same Laplace transform of the other function. So we conclude that Y delta of t is actually equal YH of t. And that is this exercise. So the characterization of the impulsive response, the impulse response function, is that it creates an instantaneous velocity at the time where the impulsive force acts on the system. With that, we finish this video. Hope to see you in the next video.